start with the acid-base stuff that we have that you should have picked up when you came in, and then we will switch back to, if you remember, we have to do the molarity, the parts per million, and the percent by mass problems from Tuesday. Okay, so that's sort of where we're at. But since some people may be here today that were not here Tuesday, I figured we'd start with the acid and base stuff, and then we'll go to the molarity stuff that we have to wrap up. So there are there are three different theories of what an acid and a base is, whatever the proper English term to that. You only have to know two of those theories. There's the Arrhenius theory, that's how this word's pronounced, Arrhenius, and then there's the Bronsted-Lowry theory. You do not have to know the name Bronsted-Lowry. They'll just say something like, another theory of acids defines an acid as. We're talking about this one. So you need to know both of them. In Arrhenius acid, they list a bunch of acids for you on table K. So if you don't know if something's an acid, a good place to look would be right here on table K. These are really the three tables that we deal with acids and bases. We deal with table K, which is our table of common acids. Notice they give their formula and they give you their name. So if they ask you for the name of the acid, you go here and look it up. They don't expect you to know how to name acids off of your memory. If they give you an acid and they want to know its name, it'll be found here in table K. Okay? If they give you a base, table L. Table L has the common bases, and then the other table we'll be using here is table M. So K, L, and M all deal with acid-base chemistry. There is another reference table that's relative to acids and bases, and it's table T, and it's right here, the titration formula. I'll be showing you, if you forgot how to use that, I'll be showing you how to use that again in table T. So, by definition, an acid is defined as something that when you put it in water, generates a hydrogen ion. It donates a hydrogen ion. So it's a substance that generates a hydrogen ion. Anybody know the symbol for a hydrogen ion? Yes? H+. Okay? Or, since hydrogen ions really don't float free in water, it's like an acid, if you put it in water, like this guy, it will split. It's like the Angry Bird that splits, and it'll generate the hydrogen ion and the chloride ion. Well, what makes it an acid is the fact that it generates the hydrogen ion. But if this is in water, right, and I do need to show you this just real quick. If this hydrogen ion is floating around in water with its positive charge, it's really attracted to negatives. So the hydrogen ion, after HCl splits and donates it, doesn't stay free all by itself. It attaches itself to a water molecule. And so if you generate hydrogen ions, what that ends up creating is hydronium ions. So we use these really interchangeably for an acid, because an acid will generate hydrogen ions, but if you could put on your Miss Frizzle glasses and look at a solution of hydrochloric acid, you wouldn't see H+ floating around all by itself. Recognize that. It will have attached itself to water. And so you would see the hydronium ion floating around in an acid. Not hydrogen ions, because they don't stay solo. They immediately bond to a water molecule. Okay? Does that make sense? So when you see acid, they dissociate to produce hydrogen or hydronium ions. They may ask it either way. Just recognize you can use hydrogen ions and hydronium interchangeably. They are present in a high concentration in an acid. So they generate hydrogen or hydronium as the only positive ion in solution. That's the definition of an acid. Okay? How do you know if you have an acid? Look for H first in their formula. Okay? Or, if it's an organic acid, Cu, right? Look for the Cu group. Okay? So is this an acid? No! H isn't first in the formula. Okay? H has to be first in the formula. Is this an acid? Yes. It's an acid. Okay? Okay. Or you might have something like this. That's an acid. because it has the Cu group. This is the organic acid that I know you remember looks like this. And when you put this in water, the bond breaks here, and it generates hydrogen ions as the only positive ion in solution. So Cu group or H first. That's how you recognize an acid.
Do they ever show you it and ask if it's an acid and have Cu condensed?
Yes. Yeah. In fact, if you look on table K with the acids, you see this? CH3COOH. Oh, you mean like CO2H?
Yeah.
No. They're not that tricky. So they would either give you, the organic chemist write it like this, the COOH. The inorganic chemist write it like this, with the H first, so you can recognize it's an acid. Okay? But it doesn't, when you write it like this, it doesn't give you a hint about how that COOH goes together. But they will never do CO2H. They won't do that. It'll say COOH. Okay? Was there a question back there? No? Okay, we go with that? So that's how we identify an acid. A Bronsted-Lowry acid, honestly, is really the same thing. They just call, instead of calling it something that donates hydrogen ions when you put it in water, they call it something that donates protons when you put it in water. But a proton is the same thing as a hydrogen ion. So an acid is defined as a proton donor, right? Another word for donate is lose. It loses protons when you put them in water, okay? It's really the same thing, but they use the word proton. The way I remember that is if you do acid, you're a loser. Acids lose protons, okay? If you do acid, you're a loser. Because you really are, right? Or you have a serious problem and you need help. All right, bases. Bases are on table L. I already showed you the base. Bases don't generate hydrogen and hydronium, because if they did, they'd be called acids. They dissolve, and they generate hydroxide ions as the only negative ion in solution, okay? A hydroxide ion is an OH with a -1 charge. That's what hydroxide is. It's polyatomic. It's in table E. Now, what I need to emphasize, the sun's out, what I need to emphasize, that's not what I need to emphasize, is that just because you have an OH doesn't mean you're going to give it up when I put you in water. Like, for example, alcohol has an OH, right? These guys, that's ethanol. That's what's in wine and beer and blah, blah, blah. Any type of alcohol, vodka, rum, whatever. You name it, that's in it. It's ethanol. When you put this in water, guess what happens? It just dissolves, but it doesn't dissolve into particles. You don't lose this OH. So this is not a base. Simply having the OH does not make you a base. You need to be able to give it up when they put you in water. Okay? You need to be able to release it. And alcohols don't release it. You know who does release it? Metals with OH. So you can identify a base when you have a metal with OH. For example, NaOH. Because when you put this in water, it's like the Angry Bird that splits. You get Na plus and OH minus. You donate hydroxide ions as your negative ion. That's what makes you a base. Okay? That's it. Metals with OH. So this guy, non-metal, non-metal, OH. This is methanol. Okay, this is an alcohol. It is not a base. Okay, metals with OH make a base. That's it for Arrhenius. Okay, they donate hydroxide ions. A Bronsted-Lowry base is a different definition. It's more general. It includes things that don't have metals with OH. Bronsted-Lowry base, remember Bronsted-Lowry acid was a proton loser? A Bronsted-Lowry base is a proton gainer. The proper term they use is acceptor. Okay? So it's anything that accepts protons. So what that means is in order to be a Bronsted-Lowry base, you don't need an OH. You just have to be able to get another H. You might go, oh my gosh, well, what things get other H's? There's only one you have to know, and it's given to you on table L. Can you see the base that doesn't have an OH? NH3. Because if you put that in water, I'll show you the reaction in just a minute, it takes a proton from water. It accepts a proton from water. So when you put this in water, water actually acts as an acid and loses the proton, and this acts as the base and gains the proton. And I'll show you how that actually makes OH minus anyway. Okay? So the only thing you have to know that is not a metal with OH, that is a base, is right here on the base table. They will not give you others. Okay? You don't have to sweat that. Just this guy, just NH3. But they're proton acceptors. Okay? So I taught metals with OH do it, and NH3. That's who you have to know. Questions on that? Let me write that reaction real quick, because I said I would. They do this a lot, and actually you have some, and I'll direct you to those momentarily. They give you a reaction and ask you which thing is acting as the proton donor, or which thing is acting as the proton acceptor. So this is a common reaction that they'll give you. Like I said, there are others in your practice that I've attached. Okay? The double arrow means it's an equilibrium. Don't sweat that too much right now. We're not talking about equilibrium. But how can you tell who's gaining and who's losing? Well, you do what I say, you partner them up. So who does water turn into after the reaction? And it's only going to either be one proton more, one hydrogen more, or one hydrogen less. Who does water turn into? Who does it look most like as a product? OH minus. How would H2O turn into OH minus? What would need to happen to it? Lose an H. Because then you'd only have one O and one H, just like OH, one O and one H. So in order for this to turn into that, this guy has to lose an H. If you lose H's, what are you? An acid. If you do acid, you're a loser, right? It has to lose. It's an acid. Where's its H going? How does NH3 turn into NH4+? It has to gain an H, doesn't it? This has 3 H's, this has 4. So this guy has to gain the H. Well, guess what happens? The H plus goes from there to there. So if this is the gainer, because it gains an H to turn into NH4+, it is a base. So this is your acid, and this is your base. Okay? The partner, I don't think you have to know the language anymore, so I won't even tell you. That just gets confusing. So this is acting as a base because it took a proton from water, and look what it made. Remember we said bases generate hydroxide ions in solution? This generated hydroxide ions, but it did it a different way. It didn't do it because it dissolved and split. It did it because it took a proton from water and made water turn into OH minus. Okay? So that's a more all-encompassing definition of what a base is. Okay? Bronsted-Lowry versus Arrhenius. Metal with OH or NH3. Very important. Okay. Acids and bases are blank. This means when they're dissolved in water, they conduct electricity. What's the word? Something that when you dissolve it in water conducts electricity. Electrolyte. Good. You get lots of questions. Which of the following are electrolytes? Guess what you should look for? Acids and bases. Look for H first or Cu, or metal with OH or NH3. Usually they give you H first. Okay, that's what usually the choice is. But it could be a base. It could be a metal with OH. All right? So they do that often. Let's pause for a minute. I'm going to just pause this. And I want you to do a couple questions. All right. So acids and bases react with each other. When you mix an acid with a base, that's a particular chemical reaction or process that's known as neutralization. They neutralize each other. Like when you get heartburn, everybody, it's because you have too much stomach acid. So what do you take? Tums or Rolaids, which are bases, and they neutralize the excess acid so that you don't have heartburn. Okay? So the Tums is a base, and it reacts with the acid in your stomach. They neutralize. All neutralization reactions are double replacement. They are wife-swapping reactions, where the H and the metal switch partners. Okay? The products are always salt Yeah, when I say salt, everybody thinks NaCl, but it could be any salt. Salt is just another word for ionic compound. Any plus minus, right? An ionic compound is any plus minus. So like plus metal, negative polyatomic, plus metal, negative nonmetal, right? Plus polyatomic, very rare that you see this one. Negative nonmetal, or plus polyatomic, minus polyatomic. Any of those are salts, okay? Any of them. And you also make water. Okay? So you always make salt and water. To identify a neutralization reaction, you need an acid and a base on the left-hand side of the arrow. You also need water on the right-hand side. Okay? So you can always identify a neutralization reaction because you have an acid reacting with a base, going to make water and something else. I say something else, it is salt, but it's difficult for kids to recognize salts. So don't recognize it by looking for the salt. Recognize neutralization by looking at who's reacting. You got H first or coup? You got a metal with OH? Neutralization. Bam. Okay? That's what you look for. For example, I'll make up a crazy one. CaOH2. That's a base, right? Metal with OH. That's our base. Reacts with sulfuric acid, battery acid. H2SO4. H is first. That's our acid. Guess what they do? They wife swap. The Ca switches places with the H. Bada bing, bada boom. So now you got the H with the OH, which you can write it as HOH, but that's kind of weird, right? Normally, most normal people write it as H2O. And now you got the Ca with the SO4. This is your salt, and this is water. And I'm big into balancing equations, so I need a 2 here. Okay? That's it. They're wife swap and double replacement reactions where you mix an acid with a base to make salt and water. That's all that they are. So I need you to find a neutralization reaction for me. Let's do number 73 right now, please. Do 73 and do 77. Those two, that's it. And then we're moving on. Of neutralizing is called titrating. And particularly titrating is the process when you're trying to find out what an unknown concentration is. Did you and Mr. Combs do the titration lab with the burettes and you drip the...
No.
Oh, some people say yes and some people say no. I don't know. Well, anyway, we titrated vinegar, right? We were trying to find out the concentration of vinegar because who knows what the molarity of vinegar is in acid? We didn't know. So we added base to it. Well, first we added an indicator to it that was colorless in an acid, but in a basic solution it turned pink. And then we added the base to the acid until it just turned pink. Not too much because then you over-titrate, right? And if you know the volume of your base that you add to make it neutral, and the molarity of your base, and you know the volume of your vinegar that you started with, you can calculate the molarity of your vinegar, which we did. And we had calculated our error and all that fun stuff. But anyway, the titration equation that you're going to use to calculate the unknown molarity is given in table T. It's Ma, I showed you it really already. It's MaVa equals MbVb, right? And they define the variables. This is the molarity of your acid, the volume of your acid, the molarity of your base, the volume of your base. So for example, I pulled this out of the June exam. In a titration, 50 mils of 0.026 molar HCl, what's that? Acid, right? So this is your acid data. This is milliliters is a unit of volume, so that's your Va. Capital M is your molarity, so that's your Ma. Okay? Is neutralized. You see this word? You see this word? If you see the words titration and neutralize with numbers, you got to use MaVa equals MbVb. Out of doubt. There is no other equation you're going to use. Period. Neutralized by 38.5 mils of KOH. What's this guy? Base. So this 38.5 mils of it is VB. Show a correct numerical setup for calculating the molarity of KOH. I saw titration, I saw neutralization. I'm going to write down my equation and plug in. Because when they say setup, that's all you have to do. Set it up. You don't even have to solve for X. So MA is 0.026. VA is 50. MB, don't know. BB, 38.5. Done. That's all you got to do. Okay? That is the only calculation you really have when it comes to acids and bases. Is that? Yeah?
For those questions, do you have to go as far as dividing the 38 points?
Nope. No. When they say setup, this would be 100% correct.
Would you lose credit if you divided that?
No. So if you solved for X and just did like this, fine. Okay? Do you get what he's actually doing there? Even if you kept going and actually got X, you would still get the credit. But if you only write the answer down, you won't get the credit. Okay? Does that make sense?
Yeah.
All right, now check this one out. Finish this equation. This was the second part of this question. Complete the equation in your answer booklet. Okay? So what goes in the missing line? Yep, wife swap. KCl goes there, right? This is an acid and a base. They always undergo double replacement. You wife swap them. Bye, Megan. Okay? Any issues with that? Okay. Next is indicators. Indicators are all found on table M. In general, if they give you if they don't, they just want to know, say, what color is an indicator in an acid or in HCl. If they don't give you a pH, then the way you read this table is with this column. Okay? The first color is generally the color in an acid, and the second color is generally the color in a base. So if they don't give you a specific pH, you would go, oh yeah, methyl orange is red in an acid and yellow in a base. Bromthiamyl blue is yellow in an acid, blue in a base. Phenolphthalein, colorless in an acid, pink in a base, right? That's it, okay? Litmus, red in an acid, blue in a base. So the first color is the color in an acid, the second color is the color in a base. However, if they gave you a specific pH, you have to look at this column. Okay? So if they said the pH is 5, what color is bromcresol green? Alright? So you would go to bromcresol green and you'd find where 5 falls in this range of values. Since 5 is in between 3.8 and 5.4, then your indicator will be in between these two colors. What's in between yellow and blue? Green. Okay? If you were at a pH 3.8 or below, you'd be yellow. If you were at a pH 5.4 or above, you'd be blue. Okay? So if you're at the first pH or lower, you're the first color. If you're at the second pH or higher, you're the second color. And if you're in between those values, you're in between those colors. Okay? So I have an example there, I think. And it says, what color is bromthiamyl blue in a solution whose pH is 5? Then 7, then 8. So let's go here. Bromthiamyl blue, pH is 5, right? Bromthiamyl blue, a pH of 5 is less than the first pH. So what color am I? Yellow. The first color. Yep, I'm yellow. You got it. Okay, let's go 7. 7, 7's in between. So we're in between yellow and blue. Green.
Wait, you can have that?
Yeah.
What would be between colorless and
There is no in between colorless and pink. In between colorless and pink is really light pink, right? Just that's why when you titrate, you just want that faint pink. Okay? So you don't want to get bright magenta, because then you're completely basic. You want it in between that range. They won't give you one that's in between colorless and pink. That would be silly. All right, pH 8.
What about red and blue?
Purple. Go ahead, I'm really good with colors. Keep going.
I media, so
Okay.
I can get art out of the way with this.
All right, so the next one is what? 8, pH 8. We're higher than the second color, so we're blue. I think you guys got this. All right. Final thing is the pH scale. The pH scale tells us how acidic or basic something is. As the pH increases, the solution becomes more basic. And the hydrogen ion concentration decreases, but the hydroxide ion concentration increases. We're going to diagram all this in a minute. As pH decreases, we become more acidic, so there's more hydrogen ions and there's less hydroxide ions. So in an acid, everybody, the concentration of H+, those brackets mean concentration. Concentration of H+ is greater than the concentration of OH-. So remember we said acids donate hydrogen ions? That doesn't mean that there are not hydroxide ions present. There are, but they're present in a very small amount. Okay, so in an acid solution, it's all about the H+, and there's a few OH-. In a base, it's opposite. In a base, the concentration of H+ is less than. Do you know your signs? Less than the concentration of OH-. So base is all about the hydroxides. Acid's about the hydrogens, base is about the hydroxides. If you are neutral, they are equal. Okay? So in a neutral solution, the concentration of H+ equals the concentration of OH-. Okay? Now let's draw the scale. I think you have a line. So what is neutral? What pH does that occur at? 7. So below 7 is an acid. As you go this way, you become more acidic. So that means your H+ concentration goes up. So the lower the pH, the more H+. Okay? Over here, up to 14 is generally, goes from 0 to 14. So if one question is multiple choice and they give you like a pH of 0.2, don't pick it. Or 20, don't pick it. The answer is, the pH values will always be between 0 and 14. Okay? So up here, you're basic. Okay? And when you go this way on the scale, the hydrogen ion concentration decreases. So it's like opposite. The higher the pH, the less H+. The lower the pH, the more H+. Okay? And beyond that, you need to be able to know how much more. Every 1-digit change in pH is a 10-fold change in hydrogen ion concentrations. Every time you move 1 digit on the pH scale, the hydrogen ion concentration either goes up by 10 or down by 10, depending on which way you're moving. Which way would you have to move to get more hydrogen ion concentrations? Lower pH. Lower. Right, down the scale. If you want less hydrogen ions, you move up the scale. And I think I have that here. Every 1-digit decrease in pH is a 10-fold increase in hydrogen or hydronium. Okay? For example, look at this. If the concentration of hydrogen ions is 1 molar at pH 4, okay, and sometimes it's wise to map these, like do like a number line. And if you go to pH 3, then you have to multiply your concentration by 10. So 1 times 10 would give you a concentration of hydrogen ions times 10. And then if you went to 2, you have to do another 10. So really you're multiplying by 100. It's a 100-fold increase. You've moved 2 digits. So your concentration would be 100. And if you go up the scale, let's say we were going this way. What's our concentration here? 1 molar. What if we went to pH 5? What would our concentration be? 0.1. Right? When you go up the scale, you divide by 10. Every 1 digit you go up. So this concentration would be 0.1. What if we went to 6? 0.01. Yep. Okay? You divide by 10, every digit you go up. You multiply by 10, every digit you go down.
Would they ever, like, you know, concentration? Would they ever give you, like, parts per million for one of these?
No, never. Never. Absolutely not. It would always be in terms of molarity. Okay? I want you to try, I think that's it. That's everything about acids and bases. So I want you to try just a couple with this pH and titration stuff, and then we'll go on to molarity. Okay? So let's do, can we do 3? Let's do 3. Let's do 11, 13, and 10. Or 14, sorry. 11, 13, and 14. We'll just do those 3, and then we're going to move on. So let me just pause this while you work it. So that was all we needed to know about acids and bases. But in our last video, or in our last review, we didn't get to the most important, I don't know if it's the most important part, but it is certainly highly tested about solutions. You need to know how to calculate the concentration of a solution. Okay, all of these equations are given to you in that infamous table T. Okay, not anywhere that you can see. Concentration. Okay, so there's 2 major ways we express concentration of a solution. If it's a super dilute solution, there's not a lot of stuff to dissolve. Like we would maybe use this to calculate how much lead is in our water, right? Because that's not something that's supposed to be there. And so it's going to be present in a really, really small amount. We use parts per million to represent things that are present in a small amount. That's abbreviated ppm, okay, parts per million. We could also use more commonly, and if they don't specify and they just say concentration, they want this, molarity. If they want parts per million, they'll tell you. The other way is right here, percent comp by mass. Okay, so these are the 3 ways we express concentration. If they don't specify, you're doing that one, molarity. Okay? So the equations are, from table T, molarity, which is abbreviated capital M, is the moles of the solute per liters of solution, the volume of the solution. Now, there's a couple tricks that they do with molarity. One thing they do is they give you the grams of the solute instead of the moles. And kids just try to plug in grams in the numerator, but you can't, because it isn't grams per liter, it's moles per liter. So if they give you grams instead of moles, you have to convert it. So you got to watch for that. Okay, so if they give you grams of solute, you convert it to moles before you plug it into the formula. The way you convert it to moles is by dividing by the formula mass. Okay, then plug it in. All right? So you convert it to moles, then plug it in. Do not plug grams in. Do not. That's going to be a choice. They're going to give you purposely that wrong answer because they know that's what kids do. 40 grams of NaOH is dissolved in 1 liter. What's the molarity? And 40 will be a choice. But really the molarity is 1 because the formula mass of NaOH is 40. So 40 divided by 40 is 1 mole. I said the volume was 1 liter. 1 divided by 1 is 1. Okay? So be careful. Be smarter than them. The other thing that they will do is that sometimes they give you the milliliters. They might say something like 250 milliliters of solution. You can't plug milliliters in. It has to be liters. So to go, you have to convert that to liters before you plug it in. And the way you convert to liters is by dividing by 1,000. The prefix milli means 1,000. Okay, so you divide by 1,000, so 0.250 is what you should plug in for that problem. The other thing that they will do, I will tell you, is they'll give you molarity and give you liters and ask for moles. So you'll have to rearrange this equation to solve for moles, right? Just think of this as over 1 and cross multiply. So moles is really equal to molarity times liters. That's the third little final trick that they do. Okay? Parts per million. Parts per million is equal to the mass of the solute. So this time it is mass, not moles, divided by the mass of the whole thing, which is the solution. Remember, the solution is your solute and your solvent added together. There's 2 parts of a solution. The solute, which gets dissolved, and the solvent, which does the dissolving. Okay? I have seen questions where they give you just the whole mass of the whole solution. And then I've seen other questions where they give you the solute and solvent separately, and you have to add them together to get the mass of the solution. And many times with parts per million, they give you the point just for the setup rather than the solvent. Because if you solve it, technically, well, a lot of times, even if you plugged in just the solvent, you get the wrong answer, or you get the right answer. So they give you the credit for the setup, not the solution. All right, anyway, times a million. That's why this is called parts per million. It's the ratio times a million. Whereas percent by mass is the mass of the solute, the mass of the part. And again, with solutions, that's the solute, divided by the mass of the whole, which for solutions, that is the solution. Again, it's the solute plus the solvent, and they give it to you many ways, times 100. Okay? So maybe we can walk through a couple of these just together. What the heck did I do with my copy? I'll find a couple problems, and we'll just walk through them together so that you can get an idea, because we're running out of time. Look at 30, how about, good. How about 37, 38, 39, something like along those lines. All right, so 37. How many moles of KNO3 must be dissolved in water to make 1.5 liters of a 2 molar solution? We're on 37. Every time I see a number, I stop. 1.5 liters. I identify, this is from the other one. Do you want a copy of it? Just to follow along?
Yeah.
Okay. All right? Didn't I go around and ask? Gave one to your neighbor and you did not want. What is 1.5 liters? Volume, right? That's a volume. That's the volume of our solution. Okay? And 2.0 capital M is the molarity. Capital M is molarity. Okay, that's all the numbers. Now I go to what the heck do they want to know? What the heck do they want to know? Moles. So I write down, they want to know moles. You got to write all that down when you're doing these problems. Okay? After you do that, you go through all the numbers, you've identified what they've given you. You've identified what they asked. Then you turn to table T. And you find an equation that's going to help you. Okay? When you are given or asked molarity, and you do not see the words titrate or neutralize, you are going to use your molarity formula right here on table T. Again, if you see the words neutralize or titrate, you use this one. But we're not acid-base here. We're not neutralizing, we're not titrating. Straight up this one. So we're going to use this formula. Write down that formula. Molarity equals moles over liters. Plug it in, solve for what you don't know. It's that simple. So molarity goes here. They want to know moles, so I'll give that my X, and they gave me liters. 1.5 in the denominator. Remember what I told you to do to solve this? Slap this over 1. Cross multiply, right? So X equals 2 times 1.5, so X should equal 3 moles. Okay? Not too bad. It really isn't. Look at number 38. Which sample of HCl contains the greatest number of moles of solute particles? So do you see that's 4 of these problems? That's it. You take the molarity times the volume for each one. So for each choice, they want to know moles, and for each choice, you are given volume and you are given molarity. So for each choice, you are going to find moles, right? If I just rearrange this to solve for moles, by multiplying the molarity times the liters. So how many moles are there in A? 2. Yeah, 1 times 2 is 2. How many moles are there in B? 1.5. So get rid of that one, because they wanted the greatest number. How about C? 4. Get rid of A, because 4 is bigger than 2. And how about D? 2. 2. So the right answer should be C, because that's 4 moles of particles. Okay? And then I have a parts per million. This will be the last one we do today. What is the concentration of O2 in parts per million in a solution that contains 0.008 grams, am I reading the right one? Yeah. Of O2 dissolved in 1,000 grams of water, and they want ppm, right? What they want. Who's the solute? Who's getting dissolved here? Oxygen. This is my solute. What's water? Solvent. This is why the setup is important. Because if I'm solving ppm right now, right, we know the formula is the mass of the solute. From table T, you can get it. We just wrote it down. The mass of the solute over, is it over the mass of the solvent? Oh no. It's over the mass of the whole solution. So in this case, they gave us the mass of the solvent and the solute separately. You have to add those together to get the mass whole. And then you multiply by 1,000,000. Whoops, 1,000,000. Okay? Now in this case, when it's multiple choice, it doesn't make a difference. Because I think if you divide it by 1,000 versus if you divide it by 1,000.008, you kind of come up with the same ppm. But if it's a setup question and you just put 1,000 in the denominator, you're getting it wrong. You're going to get it wrong. So you have to recognize if they're only giving you the mass of the solvent, which the solvent's always going to be water. So if they give you the mass of water, unless it's like pond water, because then that's a mixture in the solution. But if it's just the mass of pure water, you're going to have to add that to the mass of your solute to get the mass of the solution. Okay? Question, what is the answer? Nobody has a calculator? No. Do you want the answer? Let's solve it. We can't leave things unsolved. That's like unfinished business. All right, 0.008 divided by 1,000.008 times, it's 8 times 1,000,000. 7.9999936. It's 8. 8 ppm. Okay? All right. When am I having review next? Tuesday morning. Is review next. 11:30 to 2:30.
Where?
Well, I guess it's not morning. Here. 11:30 to 2:30 here on Tuesday. Okay? Any requests? I just want to do exam questions. Any requests? Next review, exam questions? Surprise you. I don't know. I think you guys got to do questions. I think it's time. I'll let you go into the class. Okay. Bye, guys. Have a great night. Oh, here.